So for doing that first one, we're writing the exponential as a logarithm, and hopefully by now we've got a nice rhythm going with that, where we know to start at least by writing log. And then the very next thing we write is the base of our logarithm, which is going to be the same as the base of my exponential, which is going to be m. So we know it's log base m of something, but I'm going to say at the moment I don't remember what that something is. What do I do if I forget? Well, I know after that something it's going to have to equal, right? So it's just really a matter of what goes into these two spots. Well, one of those I remember more easily than the other one, because I remember that log always equals the exponent. And so since the exponent is n, I know that my log will have to equal n. Notice by process of elimination I can now tell what goes inside the logarithm. So should you forget, that's the sort of thing you can do to kind of piece it together. And that's okay if you do it that way. All right, and then that second one there, we're doing the same thing but backwards. So when we write our exponential, the first thing is the base, which of course comes from the base of the logarithm as well. That should be a capital T. And yes, capitalization does matter with variables. A capital T and a lowercase t actually represent different variables. So keep track of capitalization as you go through these. All right, next thing is going to be my exponent. Well, I remember that log equals the exponent, so it must be 18, because 18 is what my logarithm is set equal to. And then finally, the only thing I haven't used yet is the r, and so it equals r. Now, having written our equation for this one, I didn't tell you what form to write it in. Some of you will have just written this equation in point-slope form. Some of you will actually have gone for slope-intercept form as well. Well, the thing is, I want you to be able to do both. So, if you wrote it in point-slope form, I now want you to write an equation in slope-intercept form. If you wrote it in slope-intercept form, I'd now like you to write it in point-slope form. I need you to be able to do both of them. All right, now let's see how we would have done that. So I hope that when you first saw this problem come up, ideally you would have actually started with the point-slope form, because I gave you a point and then we have the slope. If you're given the point and the slope, we can go straight into point-slope form. And in fact, starting with the point-slope form will even make the slope-intercept form a little bit easier to do as well. These are the two equations that we come up with. And yes, it is these two in particular, because we are given the particular point to go through. So this is the point-slope. And if you were a little bit rusty on that, having trouble finding your notes, or if you're gone on Friday, this is the formula that I'm going to when writing my point-slope form equation. And then the second one is the slope-intercept, the one that we're more familiar with, good old y equals mx plus b. But every now and then we run into the question of, yeah, I was able to use my notes to write the point-slope form, but then I didn't get how to find my y-intercept for the other one. Well, that's what we're going to take a look at now. One of the great uses of point-slope form is being able to take something where you just have some random point and turn it into the more comfortable slope-intercept. And we do that with just a little bit of algebra. Notice our slope-intercept form. What makes it slope-intercept is that there's no parentheses and it's just plain old y equals. So if I want to do that with my point-slope form, the first thing I'm going to do is I'm going to get rid of the parentheses. Well, that means it's still going to be y plus 1 on the left side. But I distribute in the negative 3, so that becomes minus 3x, negative 3x that is. And then I'm going to also do the negative 3 times negative 7. Negative times negative, of course, is plus. That's positive. Excuse me. And so that's going to give me plus 21. The last step is I do need it to be y equals instead. And so we subtract 1 from both sides. And if you do that, we end up with y equals negative 3x plus 20. That's why it's 20. That's how we know it's 20. You don't have to like graph it and then see where it crosses or anything like that. We can actually do it algebraically like this. as we go and make these graphs, make sure you are writing the actual equations above the graphing grids. That way the graphs are actually useful to look back at later. All right, so let's take a look at how we do that first one, y equals 4. Usually when people are looking at this one, the question that I'll hear is it horizontal or is it vertical? In order to answer that question, we could actually just answer it with another question, which is often the way I do things, is answering questions with questions. Where's a point where y equals 0? Well, most of you are probably thinking of this point right here. Because most people assume that that means that the y is 0, or I'm sorry, that the y is 4 when x is 0. But x can be anything, really. What if x is 1? What would y be? It'd be 4. And so if x was 1, y would be 4. What if x was 2? What would y be? 4. It's always going to be 4, right? And so pretty quickly we can see it's got to be the horizontal line. And that's why it's horizontal, because those are all the points that have a y-coordinate of 4. And then we head on to the next graph. Y equals 2 times the absolute value of x minus 3. Now this is the first one we've done in here, at least, that has the 2 sitting out front of the absolute value. So we're going to make sure we know how to deal with that. First thing, though, let's deal with what we do know. The x minus 3. Now remember that anytime you add or subtract, it shifts the graph. And if I add or subtract to the x, it moves it in the x direction. So that's either left or right. Which way does minus move it? Is that to the left or to the right? That is to the right. And that is always going to be the case. Minus is always going to the right. Plus would always go to the left. Doesn't matter which type of function it is or what else is happening within it. Minus will always go to the right. Now, adding and subtracting always shifts our graph. But the 2 out front, it's multiplying. That means it's not actually shifting it, though. So my first point, my vertex, is only going to be right 3. It hasn't been moved up or down at all. So your first point is right 3. So then what does the 2 do? Well, think about if I gave you like a linear equation, like y equals 2x minus 3. No absolute values or anything. The 2 there is your slope, right? It tells you how high you're going each time you go over 1. This is going to be the same basic idea. It's going to tell us that as I go over 1, I'm going to have to be going up 2. Up 2 over 1, up 2 over 1, up 2 over 1. And it is really just a line on the right side here. So you can go ahead and just keep doing that up 2 over 1 all the way along on the right side. And yes, it's good to use the straight edge to draw that in. But there I was just talking about the right side. What's going on the left side? Well, the reason why this does what it does here is because normally if that 2 weren't there, I would go over 1 and up 1. And what the 2 is doing is it's applying a vertical stretch to our graph. In other words, it's making it twice as tall. So where I used to go up 1, I now go up 2. We're going to do the same thing on the left side. Normally, if that 2 weren't there in my graph, I'd go left 1, up 1. Well, again, if I double the height, it's going to be left 1 and up 2. So it's still going to be doing up 2 over 1 on the left side as well. It's just up 2 and left 1 instead. And again, we can go ahead and draw the line in that goes through that. Hopefully neater than that. Now we did these 2 graphs basically as an approach to today's lesson, because today we're not just going to be graphing equations. Today we're going to be graphing inequalities. So that is, we're going to be making graphs of these relations that have greater thans and less thans in them instead of just equal signs. So these look very similar to the last 2, but you notice they are a little bit different. Write down the 2 new inequalities and then we're going to work through them. All right, so graphing inequalities, basically it's just like graphing equations, at least at the start. It's graphing an equation with just 2 extra rules to remember. That's really what it is. Okay, so the first thing I'm going to do is I'm going to treat this just as an equal sign and graph y equals 4. Well, we already know what that one looks like. We already know that y equals 4 is just this horizontal line. And so it is here. Now, think about what this line means, though. This line here represents every single point where y equals 4. But now I want to reference every single point where y can also be greater than 4. So we already got the equals. Now we also have to plot the ones that are greater than. So like this point is greater because there our y coordinate is 5. Okay, over here the y coordinate is still 5. So it's still greater, right? Up here the y coordinate is 7. Up here my y coordinate is 8. Those are all still bigger than 4, right? And I certainly do not want to have to try to plot every single point that's greater than 4, especially because there's an infinite number, because there's even like the decimals and all that stuff in the middle. That's why we shade it. The shading shows that every single point in this whole shaded region satisfies the conditions of this inequality. That is that the y coordinate is greater than or equal to 4. So shade those in as you're shading. A little shading hint, especially if you're using like an old school wooden pencil. Turn that pencil basically on its side and put that flat edge against your paper and then start shading in. You get a nice wide swath of shading going in, and it'll also be a lot faster because you're covering a lot more ground a lot faster. But don't worry, the shading doesn't have to be absolutely perfect. You don't need to make every single dot white here when you're shading in by hand. All right, now we go on to the next one. And for the next one, we would start graphing it the exact same way. We're still going to start graphing it as if it's y equals. So I'm going to start by going right 3, and then I go up 2 over 1, and up 2 over 1, and all the way along there. But this particular one, it has something else going on in it. Because right now, when you take a look at that graph, those points on that graph, those are all of the points where y actually equals that 2 times the absolute value of x minus 3. Those are all the points where it's equal. But notice in this problem, we don't want to know where they're equal. We want to know where it's less than, but not equal. So notice our first one, it had an or equals to on it. This one doesn't. So how do we show that there's this border here, this line, but it does not actually include the points that our graph does? That's where we make the lines dashed. And one way you can do that is just take the lines that you just drew in pencil and just erase little dash marks into it. You would also draw it in dashed in the first place, of course. But that's what we need to be looking at for this, is we need to be looking at a dashed line, a dashed graph, because what that's doing is that's showing that the points on that are not solutions. All right, but we still need a shade here, because there is an infinite number of solutions out there. Just we need to know whether they're above the graph that I just drew in or below the graph that I just drew in. Well, for that, it actually works the way you would hope, logically speaking. This symbol right here, do we read that as a greater than or a less than? Yep, that is a less than. And if you're having trouble getting those straightened out still, keep practicing it. Knowing those is going to help a great deal here. That is a less than symbol. What do you think? Do you think that you would shade above or below when it's less? Below, yeah. And so we're going to shade below this graph. And yes, when you're doing this on paper with your pencil, doing something like that would be sufficient. Of course, if you can get it all colored in like that, that's even better, but that's not always possible depending on the tools at hand. All right, now you'll notice that I gave you a couple rules here for graphing inequalities. They were kind of embedded in stuff we were talking about. We talked about how the greater than versus less than tells us whether we shade above or below. We also talked about how the equal sign meant to draw a solid graph, and lack of an equal sign tells us to draw the dotted graph. This is a great way to organize those things that we've touched on. This is the basic process for graphing an inequality. This would be a good thing to put into your notes there. And if you do find yourself sometimes mixing up which direction the greater than goes and which direction the less than goes, you might also add that to your table there. And you'll notice that these notes work specifically with y on the left side. As you might expect, if I all of a sudden flip the entire inequality around, the signs would change, and all of a sudden these things would change as well. So these work as long as y is on the left side, specifically actually as long as y is the only variable on the left side. If we tried to throw x over there, some weird stuff can happen too, which actually we will see here before too long. We will be messing with some equations that have x and y on the same side. But for now, this will get us taken care of. And now that we've seen the general ideas about how to graph these, I now want you to practice doing a couple on your own. So please write down and graph both of these inequalities. So for graphing that first one, remember I graph it first just as if it were y equals 3x minus 4. Notice the minus 4 is hanging on the end, and so that's telling me that I'm going to be shifting down 4. The 3, since it's multiplied by x, that is my slope, and so that tells me to go up 3 and over 1. And then in this particular case, should my line be solid or dashed? It should be dashed, yes, because it is not an or equal to. So you draw on the dashed line, and then you just have one last decision to make there, and that's whether you shade above or below. Which way do we shade in this particular first one? Above, yep. So shaded above, that's the graph you should be looking at. Now I do want to give you just one little hint on the second one. Normally when I graph absolute value, I get a V-shaped graph. This is the first one we've done together that has a negative out front. So what's the negative do? It flips it upside down. It reflects it across the x-axis. And so your graph is going to be the same kind of V-shaped graph that you've done before, just it's going to be opening downward instead of upward. All right, so now let's go ahead and make that graph. First of all, I want to know where the first point has been moved to. I want to know where that vertex is. And so I look first at what number is added or subtracted to the x, because that tells me how far I move it over. I got a plus 2, and plus 2 tells me that I'm going to be moving it left 2. Plus will always go left, remember. Doesn't matter what type of function it is. If it's left or right, plus goes left. All right, and then the plus 1, it's hanging on the end. So that is going to be moving it up 1, just like it always has. Notice that the negative out front here didn't change either of those. It has no effect on what behavior the shifts have. All right, so I go left 2, up 1, plot the point there. And then what the negative does do is that it means that I'm not going to be doing that. Instead, I'm going to be doing this. Specifically, it's going to be a ratio of 1 to 1. So it's going to be down 1 over 1, down 1 over 1, down 1 over 1, and so on both sides. And then, of course, the last question before we actually draw it in. Should it be solid or dashed? It isn't or equal to. Since it can be equal, yes, it should be solid. Because we're saying that all of the points on the graph where it's equal also satisfy this equation, or this inequality. All right, one last question from there is the shading. Will this one be shaded above or below? It will be below, yes. And we know it's below because this is a less than symbol, and less than means under, means below.